energy required for the ethane molecule to rotate about the carbon-carbon bond axis is called as the torsional energy. There are two conformations, eclipsed and staggered, and there are two ways in which you can represent it as one is Newman conformation and other one is Sawhorse formula. Vicinal dihalides means two halogen atoms are attached to adjacent carbon atoms. From alkynes we can prepare alkenes, and from alkenes we can prepare alkanes. Hello everyone, this is Ambali Unnikrishan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 3 of the chapter Hydrocarbons. So in the last session we completed the physical properties as well as the chemical properties of alkanes, right? So in today's session we are going to study about the conformations of alkanes, and we are going to start about alkenes. The next one is alkenes, right? So the nomenclature of alkenes, the methods of preparation and physical properties of alkenes, okay? So there is one small topic remaining in alkenes, that is conformation. Then we'll start with alkenes, okay? So what is exactly conformation? What does this word conformation of alkanes or conformation in alkenes means? Let's see. Different spatial arrangement of atoms of a molecules which can be converted into one another by the rotation around a CC, carbon-carbon single bond, are called as conformations or conformers or rotamers. So all these three names can be used: conformations, conformers or rotamers. So how they are spatially arranged? That means in each of this organic compound, that is in alkanes, how the atoms are arranged in space, and from one arrangement to another arrangement, how we can rotate it about a carbon-carbon single bond. About this we are discussing in conformations of alkanes. So in here we are going to study the conformations of ethane, that is CH3CH3, right? In ethane, the two tetrahedral methyl groups can rotate around the carbon-carbon single bond to yield several, that means infinite arrangements. Out of these two extreme arrangements are eclipsed form and staggered form. So the example we are going to take here is CH3CH3, that is ethane. Okay, so it can have infinite number of arrangements in space. Why? Because there is only one carbon-carbon single bond. As you can see, CH3 and CH3, right? So it can rotate about this carbon-carbon single bond. So that means that it can have infinite number of arrangements. So out of these two extreme structures, we are going to see one is eclipsed form and the other one is staggered form. Okay. So first let's see eclipsed form. So in this form, hydrogen atoms attached to two carbon atoms are close together as much as possible. So in eclipsed configuration or eclipsed form, the hydrogen atoms of both of the carbon atoms, we are taking the example of ethane here, right? So in this case, the hydrogen atoms of both these carbon atoms will be represented as close as each other. So you can see this is eclipsed conformation. Okay, so how can you represent the eclipsed form? Let's see. So as you can see here, the one circle you can see, so this circle represents one carbon atom and on which you have 1, 2 and 3 hydrogen atom. Right, and in the middle you have another carbon atom which is represented, okay, by a dot, and on that you have 3 hydrogen atom. And as you can see, this hydrogen atom of one carbon atom and this hydrogen atom of another carbon atom is as close as possible to each other. So this type of representation is called eclipsed. So that means this is one carbon atom which has 1, 2, 3 hydrogen atoms, and this is of the second one, and they are very close with each other, as you can see, right? Okay, so in this case, the hydrogen atoms of both the carbon atoms are as close as possible. So this is called as eclipsed form or eclipsed conformation. The next one is staggered form. Now what will be staggered? That yes, the hydrogen atoms of the carbon atoms will be as far as possible. So in this form, hydrogen atoms of the two carbon atoms are oriented in such a way that they lie far apart from each other. So this is what staggered structure is. You can see here, yes, this circle stands for one carbon atom, right? And you can see 1, 2 and 3 hydrogen atoms of that carbon atom. And the next one is represented in the center, 1, 2, 3 hydrogen atom of the second carbon atom. And you can see they are as far as possible from each other. Right, okay, this is how you represent the staggered form. And these two forms can be interconverted by rotation of 60° about the carbon-carbon bond axis. So that means that if you can interconvert them, that is from eclipse to staggered, you can convert it, that is interconvertible by the change in angle. So that means that you can change it from one form to another by rotating about the carbon-carbon single bond. Right, so I hope the two forms are clear, eclipsed and staggered. In eclipsed, the hydrogen atoms will be placed as close as possible, and in staggered they'll be far apart. Right, then you have one more, that is skew conformation. So that is any other intermediate conformation between eclipsed and staggered. Okay, so we studied in eclipsed hydrogen atoms will be close together, and in staggered it will be far apart. In between them, okay, all other conformations in between them are called as skew conformation. Now, the next important point is the staggered conformation is more stable than eclipsed conformation because the energy associated is minimum. The repulsive interactions between the hydrogen atoms attached to the two carbon atoms are minimum due to the maximum distance between them. So, we already know that if the energy is minimum, the stability will be high, right? So, in staggered conformation, as you can see here, the hydrogen atoms are placed as far as possible. So, the repulsion is minimum, right? If they are placed away from each other, their repulsion will be minimum, energy will be minimum, that means stability will be more. So, that is important. When you compare eclipsed and staggered conformation will have more stability due to less repulsion and maximum distance from each other, right? The relative stabilities of ethane are in the order, yes, staggered, then skew and eclipsed. Okay, so staggered conformation will have the highest stability, then skew conformation, and in the end you will have eclipsed conformation. Right, okay. Now what is torsional angle? The angle of rotation about carbon-carbon single bond is called as the torsional angle. So this angle you can see in between these hydrogen atoms, the bonds, right? So that angle about which we rotate the carbon-carbon single bond, right? So that angle is called as the torsional angle. Now, torsional strain, the repulsive interaction between the electron clouds which affect the stability of a conformation is called as torsional strain. So, it is the repulsive interaction between the electron clouds, right? So, that means this electron clouds of this hydrogen, they'll have a repulsion between each other, right? So, it is called as the torsional strain. And one more is there, it is torsional energy. Energy required for the ethane molecule to rotate about the carbon-carbon bond axis is called as the torsional energy. So, the energy required to rotate it is called as the torsional energy. So, even these three are important, the torsional angle, torsional strain and torsional energy. Now, the next one is Newman projection and Sawhorse projection. So, we studied about the two different conformations of ethane. One is staggered conformation and the other one is eclipsed conformation. And the staggered and eclipsed conformation, we can represent it in two ways. One is using Newman's projection and the other one is Sawhorse projection. So, the Newman projection we have already studied just now. In this method, carbon atom nearer to the eye and the groups attached to it are represented from the center of the circle and lines attached to the center, while the distant carbon atom and the groups attached to it are represented by the circle and the lines attached to the circumference. So, we have already studied this. That means if there are two carbon atoms, the carbon atom which is nearer to us is represented in the front. That means inside the circle from here, those three hydrogen atoms are represented. And the carbon atoms which is far away from you, that is represented as a circle, and from the circumference we draw the how many hydrogen atoms are there. So, this is how you represent the eclipsed, how the hydrogen atoms will be close with each other. The same follows for the staggered also, but the hydrogen atoms are placed little farther away. Right. Now, this is Newman projection. The next one is Sawhorse formula. So, this is a 3D structure. In this form, front carbon is shown at the lower end of the line, while the rear carbon at the upper end. The three lines attached to each carbon are at an angle of 120 degrees. So, in this case also, how we are going to represent it? Yes, one carbon will be towards us, the other carbon will be away from us. So, that carbon which is nearer to you, that is represented in here. Okay, that is below. Okay, so if this is the line, The one near to us is placed here. The carbon which is far away is placed here. And the 3 hydrogen atoms are represented in 120 degree with each other. And here also you can see. So this is your eclipsed conformation. Now how will you draw the staggered for this? The same way, the carbon away will be represented here, near to us will be represented here. But what difference you can see here? In this case, this part is just the same here as well. But to represent that they are far apart, these hydrogens is represented in the opposite way. As you can see in here, this hydrogen is represented on the top, and in here it's just the opposite of that. So this is the eclipsed conformation and this is the staggered. So what you have to understand, there are 2 conformations, eclipsed and staggered, and there are 2 ways in which you can represent it as. One is Newman conformation and other one is Sawhorse formula. So these 2 you can represent it. So I hope how you have to represent eclipsed and staggered is clear, right? So this is the conformations in alkanes. Now we are going to start with alkenes. So you already know what is alkenes. Those are organic compounds which contains at least 1 double bond, right? So alkenes are unsaturated. Unsaturated means it stands for double or triple bonded system. Aliphatic hydrocarbons containing 1 carbon-carbon double bond. Right, okay, and they are also called as olefins because lower membranes reacts with chlorine to form oily products. As they form oily products, they are also called as olefins, and the general formula for them is CnH2n. So for alkanes it is CnH2n plus 2, alkenes it is CnH2n. Okay, so I hope that is clear. Now let's learn the nomenclature. Already we have studied this in organic chemistry chapter as well as alkanes, right? So let's see. CH2 double bond CH2. As you can see, how many carbon atoms are here? 2. So the root word will be eth, and as it is a double bond, yes, the suffix will be ene, ene. Right, in the case of alkane, it is ane, ane. Here it is ene. So what will be the IUPAC name? It is ethene. Right, and the trivial name or the common name is ethylene. The next one is CH3, CH double bond, CH2. So the double bond is present here. So that means the numbering should be done from this side. 1, 2, 3. Right. Okay. So how many carbon atoms are there? 3. And it is present on the first carbon atom. So it is propene, or else you can write prop1ene. Right. As it is on the first carbon atom, it's not necessary to write that. Now the next one is CH3, CH2, CH double bond, CH2. Again double bond is here. So 1, 2, 3 and 4. Right. So how many carbon atoms are there? 4. So root word is but and it's present on the first carbon atom. So but1ene. Right. The next one, CH3, CH double bond, CH2. Again, we start numbering from this direction. So again, it is but1ene. Now the next one is CH3, CCH3 double bond, CH2. So in this case, you can see a branch as well here. Right. So it is 1, 2 and 3. So this is how we number it, right? As the double bond is present here, we start numbering from that direction. Now what we do with the branch first? We have to name the branch first, right? So it is 2-methyl, right? This part stands for 2-methyl. On the second carbon atom, you have 2-methyl. Now we move on to the principal chain, right? How many carbon atoms are there? 3. So it stands for propene or prop1ene because it's present on the first carbon atom. So it is 2-methyl propene. Right. So I hope this is clear. So this nomenclature you have already cleared with. So you just have to remember the root word plus the suffix should be used. The suffix will be ene. And if there are any branches present, the name of that specified with the position should be written as the prefix. I hope it is clear. Now moving on to the methods of preparation of alkenes. The first method is from alkynes. So when we were discussing about the preparation of alkenes also, I told you from alkynes we can prepare alkenes, and from alkenes we can prepare alkanes, right? Okay, so let's see. Alkynes on partial reduction with hydrogen in the presence of Lindlar's catalyst. What is Lindlar's catalyst? Is palladium supported over calcium carbonate, which is deactivated with quinoline or sulfur, which gives cis-alkene, okay? So again, from alkynes, how you can prepare alkenes? Right, alkynes is triple bonded system to which we add hydrogen, the bond will be broken and you'll get a double bonded system. That means alkenes. So for that, we are adding hydrogen in the presence of Lindlar's catalyst. So that is also important question. What is Lindlar's catalyst? So it is palladium supported over calcium carbonate, which is deactivated by quinoline or sulfur, and you obtain an alkane. And the important part is it is a cis alkane. Okay, so cis alkane and trans alkane also you have already studied in your organic chemistry chapter. So let's see here. Alkyne. So there is a triple bonded system, alkyne, right? And to which hydrogen is added in the presence of palladium supported over calcium carbonate, which is deactivated by quinoline or sulfur. So that means that it's Lindlar's catalyst. What is that you are going to get here? A cis alkene. So why is it called a cis alkene here? As you can see, the alkyl groups and two hydrogen groups are here. So this alkyl groups are on the same side and the two hydrogen atoms are also on the same side. Hence we call it as cis alkene. Right. For example, if I am taking ethine, okay, this is ethine, CH triple bond CH. As you can see, there are only two carbon atoms, so it is ethine. Addition of hydrogen in the presence of Lindlar catalyst will give you CH2 double bond CH2. So in this case, we cannot mention whether it is cis or trans. As you can see here, CH triple bond CH, to which hydrogen is added. Hydrogen is added means this bond is broken, one hydrogen added here, one hydrogen added here. So what is that? You are going to get CH2 double bond CH2, that is ethene. Right. Another example is propine. CH3, C triple bond CH, to which hydrogen is added, one hydrogen added here, one hydrogen added here. So what you will get? CH3, CH double bond you will get, double bond CH2, that is propene. Okay, so I hope it is clear. And another important point is that through this method you get cis alkene. Right. Now, alkynes when reduced with sodium in liquid ammonia forms trans alkene. So we understood the method by which we can form cis alkene. Now how can we form trans alkene? It is by reacting alkynes in the presence of sodium in liquid ammonia. So again we have taken alkyne here. Okay, we are going to add hydrogen in the presence of sodium in liquid ammonia. What happens? You will get trans alkene. Trans alkene means one alkyl group is here. The other alkyl group is present on the opposite side, right? And one hydrogen here and other on the opposite direction. So in that case, it is called as trans. As you can see, here it is present on the same side. Here it is on the opposite side. So this is called as trans alkene. So how you can obtain trans alkene? By addition of hydrogen in presence of sodium in liquid ammonia. And the cis alkene is obtained by hydrogenation in the presence of Lindlar's catalyst. So I hope that is clear. Now the next method is from alkyl halides. So we have already discussed what is alkyl halides in the alkanes, right? So let's see. When alkyl halides are heated with alcoholic potash, dehydrohalogenation take place. So what is dehydrohalogenation? So as I already told you, D means we are removing something. Hydro stands for hydrogen. Halogenation means removal of halogen. So dehydrohalogenation means removal of hydrogen and halogen. That means in general I can say HX will be removed. Okay, and which gives alkenes. In this reaction, hydrogen is removed from the beta carbon. Hence it is also called as beta elimination reaction. So let's see. So this example we have taken here, it is CH3CH2X. Okay, CH3CH2X. So this is an alkyl halide. That means instead of CH3CH3, one hydrogen is being replaced and one halogen is added. That's how you got this. Okay, so from this the halogen is being attached to this carbon atom. So that carbon atom is the alpha carbon atom to which the halogen is added. The adjacent one is called the beta carbon atom. So why it is called beta elimination? Because the hydrogen atom will be removed from the beta carbon atom. Okay, so what happens when it reacts with alcoholic KOH and we are heating it? Okay, alcoholic potash means alcoholic KOH. What happens? This one hydrogen and one halogen. That is what I told you. HX will be removed, right? So this part will be removed. So when something is removed, what happens? Yes, the valency should be maintained. So you can remember in that way what happens? It will become a double bonded system, right? So two of this is removed, HX is removed. What is pending here? CH2, CH2, and this becomes a double bond, right? So you get this. So that is why it is called as a beta elimination, because the hydrogen is removed from the beta carbon atom, right? So this this is the preparation from alkyl halides, and the reagent is alcoholic potassium hydroxide. Halogenation follows the order tertiary alkyl halide, secondary alkyl halide, and primary alkyl halide. So if you have alkyl halides which are tertiary, secondary, and primary, the tertiary one will undergo reaction much faster, and the rate of reaction varies with the halogen also, which one we are taking. Iodine undergoes the highest reaction, then bromine, and then chlorine. Okay, so this is a general representation we have written here. For example, if we are taking CH3, CH2Cl. Okay, so the halogen I have taken here is Cl. What happens in presence of alcoholic KOH? If you are heating it, what happens? H and Cl will be removed. Hydrogen dehydrohalogenation, right? HX will be removed. You will get CH2 double bond CH2. Okay, so this is the next method. Now the next one is from vicinal dihalide. Now what is vicinal dihalide? Vicinal dihalides means two halogen atoms are attached to adjacent carbon atoms. Vicinal dihalide. Dihalide means two halogen atoms will be there. Halide stands for halogen. And those two halogen atoms will be placed on the adjacent carbon atoms. So for example, you can see here CH2Br, CH2Br. One bromine is present in this carbon, one bromine attached to this carbon. So those carbons are adjacent to each other. So this is called as a vicinal dihalide. Okay, so this is a vicinal dihalide. It reacts with zinc to form alkene. Dehalogenation reaction take place. So dehalogenation means we are going to remove halogen here. So the vicinal dihalide, the halogen is present, no, Br2, that will be removed by the reaction with zinc. So what happens? You will get ethene, that is your alkene, and Zn Br2. The zinc will combine with the bromine which is removed from here. So I hope that is clear. Now let's take another example. Even this is an example of a vicinal dihalide, right? One on this carbon and another one on this carbon, which is adjacent to each other. Okay, to this we are adding zinc. What happens? Br2 will be removed and attached with zinc. You will get zinc bromide, and what will be left here? From where the bromine is removed, you will get a double bond there. CH3, CH double bond, CH2, that is propene. Okay, so I hope that is clear. So that is the method of preparation from vicinal dihalide. The next one is from alcohols. When alcohols are heated with concentrated sulfuric acid, they undergo dehydration to give alkenes. Okay, so when alcohols are heated with concentrated sulfuric acid, it undergoes dehydration. So what is happening here? Dehydration means, yes, removal of water will take place and you will get the corresponding alkene. So let's see. Take the example here, RCH2, CH2OH. So this OH you can identify, it is an alcohol. So what happens in presence of concentrated H2SO4? We are heating it. What happens here is, this OH and one hydrogen atom will be removed. So that means H2O will be removed. What happens? You will get a double bond there, right? And water will be removed. So for example, if we are taking this one, okay, it is CH3CH2OH, that is ethanol. Okay, and as you can see here, the alpha carbon atom will be the one to which the OH group is attached. So this is your alpha carbon and this is your beta carbon. So in presence of concentrated H2SO4, we are heating it. H2O will be removed. So the hydrogen again will be removed from the beta carbon and OH will be removed from the alpha carbon, right? So what happens is H2O will be removed. What happens? CH2, and you have CH2. What happens here? You will get a double bond here and water will be removed. Okay, so I hope this method is also clear. Now moving on to physical properties of alkenes. It's quite similar with what we have studied in the case of alkanes also. The lower members or the first three members are gases, the higher or the middle ones are liquids, and the higher ones are solids in nature. So the first three members are gases, next 14 are liquids, and the higher ones are solid in nature. The ethene is a colorless gas with a faint sweet smell. Ethene is the first member, right? Do we have methane? No, right? The first member is ethene. Ethene is a colorless gas with a faint sweet smell. All other alkenes are colorless and odorless, insoluble in water but fairly soluble in non-polar solvents like benzene, petroleum, ether, etc. Okay, so as we have studied in case of alkanes also, they are not much soluble in water but they are readily soluble in non-polar solvents like benzene or ether, right? Then the boiling points of alkenes also increases with increase in molecular molecular mass and have higher boiling point than branch chain alkenes. Even this we have discussed in the alkanes part also. That is, when molecular mass increases, the boiling point also increases. Why is that? Because the molecular mass is increasing means, yes, it is becoming heavier and heavier. So it becomes difficult to convert it from the liquid state or the solid state to the gaseous state, right? But in the case of branch, when the branch increases, what happens? Yes, the surface area decreases and it becomes easy to vaporize it. Hence, when molecular mass increases, what happens? Boiling point increases, and when the branches increases, the surface area decreases. Hence, the boiling point also decreases. So, I hope the physical properties is also clear for you. So, in the next session, we are going to study about the chemical properties of alkenes. So, in today's session, we covered alkenes. Yes, the introduction to alkenes, nomenclature, the methods of preparation, 4 different methods we studied, right? And also the physical properties of alkenes. Now, in the next session, we'll finish off the chemical properties and move to alkynes. Okay, so I hope the topics we have covered in this session is clear for you. So that's all for today. Thank you.